Hello, everyone. Welcome to Hadoop Operations, Best Practices from the Field. First, a quick introduction about myself. My name is Chris Naroth. I'm a software engineer on the Hdfs team at Hortonworks. I'm an Apache Hadoop committer and PMC member. I'm also an Apache Software Foundation member. And some of my major contributions have included Hdfs Ackles, Windows compatibility work, and various operability improvements. Before I worked for Hortonworks, I worked for Disney, and I was responsible for their initial deployment of Hadoop. And as part of that, I worked very closely with the systems engineering team that was responsible for maintaining Disney's clusters. And so I do have a tendency to think back to that old team and constantly wonder if there's something I can do now as a software engineer working on Hadoop that would make their lives better. I don't see in the audience right now, but hopefully we'll be joined later by Suresh Srinivas, who is one of the founders of Hortonworks and has experience supporting some of the world's largest clusters at Yahoo. Together, the two of us have experience supporting Hadoop since 2008. For today's agenda, I'd like to start by sharing some analysis that we've done of support case trends at Hortonworks. And when we look at that analysis, we're going to see that there are some common patterns that emerge around support cases. And then that's going to lead into a discussion of some best practices around configuration and some software improvements that help our ability to support the product. And then in the second half of the talk, I'd like to move into a discussion of a few recent features in HDFS that can help prevent problems in the first place, or make recovery easier, or just help manage day-to-day maintenance of a cluster. So let's dive into that support case analysis. The data source for this chart is the entire history of support cases at Hortonworks. And along the x-axis is time, basically month, and along the y-axis is the proportional amount of support cases reported against a specific component of Hadoop. And I've filtered out these results so that we focus on what we call the core of Hadoop: Hdfs, Yarn, and MapReduce. There are a lot of other pieces to the Hadoop ecosystem. They're also represented here, but they're grouped into a single line on this graph, other 37 components. And what I find interesting about this is that we see a trend over time stabilizing at around 30% of all support cases are driven from these core components. And intuitively, that also makes sense, because if we think about it as the core components, these are the components that are going to exist in practically every deployment. As you rise up the stack, deployments start to customize and vary the components that are deployed depending on what their specific use cases are. For example, one deployment may or may not have HBase, depending on whether or not it has a use case for HBase in that environment. The second chart here, again, is taken from the same data source, but this time we're looking at an analysis of the root cause category for each of those support cases, again, in those three core components of Hdfs, Yarn, and MapReduce. And there are a whole host of other root cause classifications that we use in our tracking system. I've chosen to limit this down to just the most significant ones, just to make this chart clearer. And the pattern that we start to see here is that a lot of support cases are driven by misconfiguration issues or documentation problems of some kind. We have separate categories for things like documentation gap versus documentation not used. Documentation not used can often indicate that it's hard to find documentation in the first place. This is another interesting point about this is that I gave an earlier version of this talk at Strata last year, and for this time around I wanted to refresh the data and see if anything had changed. And what I did notice is that there is a slight bump down proportionally in the areas of misconfiguration, documentation, and also product defect. And of course, those are areas that we do want to focus on. So we are seeking to improve in those areas, and it's good to see those things pay off. Thank you to the audience member who reminded me to click that. this is the chart we actually want to look at. So here's where you see configuration and documentation showing up as major issues. So the conclusions that we can draw from that are that core Hadoop components, HDFS, Yarn, and MapReduce, they're used across all deployments. Therefore, they receive proportionally a high amount of the support case load, and therefore it does make sense to invest a lot of effort in improving in those components. We see that misconfiguration is the dominant root cause. We see documentation is a close second. And so based on that, we're constantly seeking to improve the code to help manage operational issues, whether that means helping with diagnosis or making it easier to recover from an existing problem or just provide more visibility into what the system is actually doing. A side note to all this as well is that we're trying to incorporate all these best practices back into Apache Ambari. Apache Ambari is the open source tool for deployment and management of Hadoop clusters. And by putting best practices in there, it reduces burden on administrators to have to remember what are good configuration settings. So with that, I'd like to move into a discussion of some common configurations that we continue to see as support cases come in. First, a little bit of a word on hardware and cluster sizing. Our recommendations are based on observations that larger clusters, meaning clusters with a greater number of nodes, do have a tendency to heal faster compared to clusters composed of a fewer number of nodes that are larger. So the part of the reason for this is if you think about a failure at a single data node, there's a drastic difference between a data node with 8 disks failing and a data node with 16 disks failing. The data node with 16 disks, it's much more likely that that would end up causing more re-replication activity as HDFS tries to restore every block to a healthy 3-replica state. Spreading across more racks also gives you a greater number of failure domains. So this is about protection against entire rack loss. We recommend getting good quality commodity hardware. We like to remind people that commodity does not necessarily mean low in quality. It just means that it is common hardware. It's not necessarily specialized, but do get good quality hardware. We recommend that as you're growing a cluster, before you consider upgrading the SKU, before you consider scaling up in individual nodes, it's good to get to a base of 30 to 40 machines spread across 3 to 4 racks. And again, that goes back to the earlier point about smaller clusters needing having clusters composed of a greater number of nodes, giving you a greater tolerance for failure. We have some recommendations on, also we recommend that you use a pilot cluster as you're getting started with Hadoop. There's a base recommendation of hardware, and then depending on your workloads, you may find that you want to tune it one way or another in terms of CPU or memory or storage, depending on your specific workloads. And it's good to have a pilot program to try to identify those things early, and then that informs your later purchasing decisions for production clusters. I've left a URL here with more details about the hardware recommendations. Next, I'd like to talk about some common problems around Jvm tuning. We recommend running all of the Hadoop daemon processes with a 64-bit JVM. We used to have a recommendation around turning on a JVM option for compressed OOPs, or compressed ordinary object pointers. And this is a technique that the JVM can use to represent managed pointers as 32-bit offsets from a base 64-bit heap address, as opposed to representing every single pointer in memory as 64 bits, which can cause some overhead if you're comparing a 32-bit JVM to a 64-bit JVM. The nice thing is that this is now something that is on by default in recent JVMs. So if you're using a JVM Java 6 release 23 or later, then this is probably not something you need to look at. It's just going to be on by default. For Java heap size, we recommend that you set the maximum heap and the minimum heap, or the initial heap, to the same value. And the reason for this is because if those two values are different, you can see some surprising results. You can run into a state where, say, a name node is running for a long time and appears to be perfectly healthy for a long time, and then for whatever reason it crosses the threshold and it needs to reach out to the OS for more memory, and all of a sudden, unexpectedly, you've gone to the OS for a very large malloc call, and that may be happening simultaneously with a really important RPC call, so you may see a spike in latency for that RPC call. Another problem you can run into is that if you've accidentally configured a daemon to allocate too much memory, then you could, over time, all of a sudden have the Linux killer step in and kill your process when you thought everything was running fine. If you set these values to the same thing, then the allocation will just happen eagerly right at the start of the process, and you won't have that issue. If you don't have enough memory in that case, then it's fail-fast behavior because the daemon will just not start up in the first place. We have some recommendations on tuning the garbage collector. We have concurrent mark and sweep. We recommend that. We recommend setting parallel GC threads. The note here says high N on name node and job tracker or resource manager. Recent deployments I've been looking at, we use a value of 8 for N. You can turn that up if you're running on particularly strong hardware for the name node, for example. And also, to help debugging, we recommend that you turn on garbage collection logging. This is something that can be very helpful if you get into a situation where an important daemon is turning on garbage collection. That'll tell exactly when garbage collections are happening, the duration of each one. It will tell you the heap size, the available memory before the garbage collection and after. So you'll get a sense of whether the garbage collections are actually being effective in reclaiming any memory. Error file, this will point to a file that the JVM will use to dump out information if it crashes. For example, if something were to go wrong in the native code layer of Hadoop, something bad enough to cause the seg fault, this is where information would get dumped on some backtrace information. And also, it's very helpful to turn on heap dump on out-of-memory error, so that if you are in a situation where you're running out of memory, this will give us information on exactly what kinds of objects are consuming the most amount of memory, and that will likely give us some hints about what's going on in the process and how we can help you tune it so that that doesn't happen. Name node highability was a very hot topic a few years ago. There were a couple of different architectural options that you had there. At this point, the recommended HA architecture is to use Quorum Journal Manager. And there is additional documentation on this on the Apache site. But to summarize, in case you're not familiar with that, the Quorum Journal Manager architecture deploys an active standby pair of name nodes and offloads edit logging to a separate set of daemons called the journal nodes. So we're capable of failing over in case the active name node goes down. Clients also are aware of failover and have the capability to switch over to the new name node so that things like jobs in progress don't experience a failure. We have a note here about the open file descriptor ulimit. We recommend increasing this. Sometimes you see a default of 1024 in deployments. It's good to kick this up to 64K, especially on the master nodes. And this is a side note, not even necessarily related to Hadoop, but it's always a great idea to put configuration files into version control. You'll be able to look back on history of changes, and you'll have a lot easier time restoring to a last known good state in case something goes wrong in a configuration change. On the data node side, we have a feature called disk fail in place. And this feature allows a data node to keep on running even if some subset of its disks have failed. And this is something that we see as especially important if you're running dense nodes, meaning nodes that have a lot of disks. If you can imagine, say, a node running with 16 drives, and let's say 2 of them fail, you'd probably prefer to just keep running with 14 drives in service for that data node, serving clients, rather than shut down the whole process and lose all 16 drives. This is off by default, but you can turn that on by setting DFS data node failed volumes tolerated in the Hdfs site XML, and that's set to the number of volume failures that you're willing to tolerate. Beyond that number, the data node will go ahead and shut itself down. On the name node side, the name node metadata directories can be brought back into service at a later time if they fail. And this feature is turned on by setting DFS name node namedir restore to true. So if a particular metadata directory goes bad, say permissions get messed up on it, or there's legitimate hardware failure on that drive, you can now fix it, and the next time a checkpoint is created by the name node, it will make an attempt to bring that drive back into service. And the bottom line is then you can bring that drive back into service without actually incurring downtime for your name node to do a restart. We recommend taking periodic backups of name node metadata, and we also recommend setting aside plenty of disk space for name node logs. They can be verbose. They're very helpful for post-mortem analysis of problems, but we often see that installations have this too small. They choose too small of an amount of space for the name node logs. And as a result of that, they then have to tune log4j to roll log files very frequently, and you see situations where log files are rolling within a minute or two, and it just makes it much harder to debug things end to end. Something to keep in mind is that usage patterns on a cluster will tend to change over time as use cases change. So because of that, configuration may need to change in reaction to those changing usage patterns. If you have something on your schedule already for a major upgrade or just a major maintenance event, then it's good to take that time and take a pass over your configurations and see if this is a good time to tune anything else. And some things to watch out for are cluster storage, the number of nodes, the number of files in the namespace, the number of blocks in those files. As those factors all grow, there will be a tendency for the name node to need more heap to store that information. So you may want to go back and tune the maximum heap that you're allocating to the name node. Similarly, there are parameters for tuning the name node's handler count. This is the number of threads that the name node will use to process inbound RPC requests. As load increases, you may find that you want to tune that number. A similar property on the data node side is the number of receivers. This is the number of threads that will be used to process transfers of block data. We recommend monitoring hardware usage for your workload over time, and this is going to tell you if when it's time for your next purchasing decision, if you need to expand a cluster, do you need to make any adjustments to the hardware profile that you're buying? Do you want to go heavier on disk, or do you want to go heavier on RAM, for example? And Hadoop does expose an awful lot of metrics. There are some pure Jvm metrics to be aware of, which are garbage collection related, memory related. These are very useful for pretty much any Java application. And these are another way to look at, in addition to the garbage collection log that I mentioned, this is another, a more online way of looking at that information, something you can monitor. Rpc Metrics, that's something that we look at a lot. We find that very informative, especially every name node, or excuse me, every Hadoop daemon will expose a counter for RPC calls, RPC call queue depth, as well as time spent processing RPC calls, and both of those are good indicators of whether or not there's a load problem, whether or not you need to expand capacity, whether or not perhaps a client has gone out of control and needs to be stopped and reevaluate the activity that it's generating. Hdfs itself exposes a lot of metrics that are specific to it, including used storage, both in total and at individual data nodes. number of files and blocks, total load on clusters, and you can get a breakdown of individual file system operations from those metrics as well. So that'll give you some insight into what kind of activity your clients are generating on your cluster. On MapReduce or Yarn, something to watch is the utilization of container slots across the cluster. And just to conclude, I have that note here that it's good to reevaluate this stuff during planned maintenance windows that you already have on your schedule. I mentioned that increasingly we're pushing a lot of these best practices into the implementation of Apache Mbari because it takes burden off of system administrators to have to know all of this stuff. So just for a little bit of variety, I chose a screenshot here from HBase as an example. And what we see here is that Mbari is recommending, based on the hardware that it is being installed to, some good default values for HBase's memory allocation. It's also giving you the option, if you know you have some custom requirements, it's giving you the option to use these sliders to tune the settings to fit your deployment. Next, I'd like to discuss a few software improvements that were prompted directly by our experiences in a few different support cases. And we found that very often something very small on our part, a very small code change, can have a big impact on preventing problems or recovering from them after they happen. So I'm going to discuss some real incidents that we've seen and then describe how they led us to make certain code changes in the product. All right, so first, it's my public service announcement. Don't edit the metadata files, please. The name node metadata files are absolutely crucial for maintaining the state of the file system. So editing them, bottom line, can corrupt cluster state and result in the loss of your data. So please don't edit those. So having said that, let's talk about editing the metadata files. This is a real incident. There was a name node that was shut down, and then it was misconfigured to point at a different cluster's set of metadata files. So if you're familiar with the FS image and the edits file from the name node, this is a cluster that was brought down and then brought up, but pointing at the wrong set of those files. Now, when that happens, an important thing in the metadata is that there is a namespace ID, and this is a unique identifier that is assigned to each file system namespace, each cluster. It's generated at the name node, and then when the data nodes of that cluster register with its name node, the reply includes that namespace ID, and the data node will persist that locally itself, so that on subsequent restarts, the data node then presents the namespace ID. The name node can do a comparison and say, are you really a data node that should be registering with me? Do you belong to my cluster? And we can validate that and make sure that nothing is registering incorrectly. So in this scenario, the admin started the name node and started seeing these log messages about failure of data nodes to register with the name node. And unfortunately, the reaction was to edit the version file, which is the file in the metadata that contains the namespace ID, and change it to the value that the data nodes were reporting. And what happens next? Unfortunately, what happens then is the data nodes are now reporting a set of blocks that don't belong to that cluster. The block IDs are something that is persisted in name node metadata so that the name node is aware of all blocks that are tied to all files. The name node rightly replied to these data node messages and said, this is not a block that belongs to the file system anymore. Must have been deleted. Please go ahead and delete it. So something that we learned from this is that a very valuable, very simple change, it can be valuable on startup of a name node to just pause deletion of blocks for a little while. So that if somebody makes a mishap like this, we can react to it and shut down and correct problems like that. This is something configurable. You can tune the amount of time it takes before blocks start deleting. There was a subsequent enhancement in which we actually exposed on the name node web UI the time when block deletions would start happening. So I'll just quickly show that. This is the Hdfs web UI, and I've pointed out now just a very small enhancement that shows the time when block deletions will start. I said earlier, very small changes can have a big impact for operations. All right, and speaking about deleting data, Hdfs is well known for being a scalable system. One of the things it's super awesome at is scaling deletes. And this can be a really scary situation if someone accidentally deletes the wrong thing, because attempting to recover from that, then it could involve undeleting individual block files at individual data nodes, getting them moved back into the directory structure expected by the data node, and then even possibly some metadata editing. Don't do it, which we would need to get the delete operation out of the edit logs there. Very tricky to recover from. So we generally recommend as a best practice, keep trash enabled. Trash basically translates deletes into renames, and then the name node will come along later at some later time and reap away the files and really delete them. So here's a real incident. There was a customer running, and they had one of these accidental deletions. They kind of panicked and said, let's shut down the whole cluster and call support. And unfortunately, the support engineer, and this is very natural, the support engineer said, let's restore from trash. Let's start back up so we can do that. What happens next? Well, they were deleted, so the trash wasn't there. In that kind of situation, it's very difficult to recover from, like I described. So I think about situations like that, and it really points out that there is a lot of danger around deleting the wrong thing. And I think about there are a couple of recent Hdfs features that really help with this. One is Hdfs Snapshots. A snapshot is a point-in-time image of part of the file system. You can create a snapshot and then refer to that snapshot at a later time, and there will be no subsequent changes shown in that snapshot. It's immutable. I'll have more details on this later. Another one is Hdfs Ackles. Ackles allow you to express fine-grained permissions on individual files. And this is basically something that you can use to really narrow down the audience of users who can delete particular files. You can apply this tool to prevent accidental deletions. The next thing I'd like to talk about is a separate case. It was an unexpected error during an Hdfs upgrade. I've left a link here if you'd like to refresh on that architecture that I described earlier. But basically what happened was, and some background first, during an upgrade of an HA name node deployment, part of the process is calling out to every one of the journal nodes, and there's a pre-step of renaming a metadata directory from current to previous.temp. This is something that's then setting it up for later restore activity if necessary. What happened was that on one of the 3 journal nodes in this deployment, the permissions somehow were messed up so that the Hdfs user couldn't actually use that directory. So after a failure on 1 out of 3 name nodes, the upgrade process aborted, and what happens next? Well, unfortunately, in this case, the root cause was not as easily identifiable as it could, and that's because we just didn't have the information that we wanted from the logs, so it was a hunt and peck exercise of trying to find if there was a disk failure or permissions problem or something else. So once again, very simple changes. These are each probably like 10-line patches that I'm talking about, and they have a big impact on the ability to understand the product. First, we changed the rename call that happens there to call down to native code. The reason we had to do that is because we can get more error information that way. And in this incident, we would have very clearly seen e-access as the error code returned from that. There was a subsequent change that, again, changing error and logging handling, but this was about clarifying exactly what code path was failing. Some of these are still works in progress. One thing I'd like to do is that if a name node or a journal node aborts, I'd like to dump out the contents of the metadata directories in the logs, including their permissions. This is something that we usually advise support to do right away if they see an incident like this. So since we always do it, it's something that can be automated. And another enhancement that I'd like to make, I'd like to implement a pre-check so that before actually attempting to rename directories on the journal nodes, we can fan out and do a basic health check that attempts to assess if the rename is going to succeed. That's kind of a tricky problem. There could still be failures due to race conditions in between checks and actual renames, but we can make a best effort there. Next, I'd like to move into discussing a couple of features that can help improve production operations. And first, more details on Hdfs Ackles. They extend the natural POSIX permissions model that Hdfs has had for a long time to allow different rules for specific named users or named groups. If you've ever used POSIX Ackles on a traditional Linux file system, then the good news is that you already know how it works in Hdfs too. Let's say, as an example, there's a requirement that a sales department has a single user and that user wants to control all modification to a sales data file. There are other members of a sales department that needs to view the data but not modify it, and everyone else in the company should have their access completely blocked to this file. And that's something that's pretty easily expressed in plain POSIX permissions. We have our sales data file. We have our user, Maya, who owns the file. We've assigned read-write permissions to Maya. We have our group sales, and we've assigned read permission to sales. And note in the other area, nothing. But let's say there's a problem. Let's say requirements change, and now the department has expanded. It's no longer feasible for Maya, just one user, to control that file completely. So instead, we want to say that Maya, Diane, and Clark are all allowed to make modifications. Additionally, there's a new group called executives that should be able to read the data. This is something that you cannot express in the traditional POSIX permissions model because it only allows one group and one user. In practice, I've seen people work around this by introducing a lot of artificial groups that contain subsets of various users, but that gets very cumbersome to manage. Instead, you can use Hdfs Ackles to express that you want a particular set of permissions applied to a specific named user or named group. And I'll demonstrate that by walking through some of the CLI tools that are used for interacting with Hdfs Ackles. So here we see set fackle, set file ackle, and we're saying assign to the group named execs read permission. Next, we'll turn around and say get fackle. And unfortunately, the formatting is not doing the line breaks correctly here. So the real output is not this one ugly line. It's nicely formatted. But if you look closely in there, you can see that the output, in addition to those traditional permissions, we see group execs read. And in addition, if you want to know if a particular directory or file has Ackles set, the output of ls has changed so that there is this little plus sign appended to the permissions. And that's your cue that you can get more information by running get fackle. We recommend that you start with traditional Hdfs permissions to model your requirements and then use Ackles for one-off exception cases. That's because Ackles have a higher memory requirement compared to a plain inode in memory. Hdfs Snapshots are a read-only point-in-time image of part of the file system. I'm going to walk through, and interesting, very importantly, these are they perform well. Creation is instantaneous. It doesn't involve a lot of copying of data, so it scales well. I'm going to walk through an example quickly. Let's say there's a daily feeds directory, further broken down by date, a very common pattern, and somebody accidentally deletes something. Well, if you have a process in place where you first create a snapshot, and that involves allowing snapshots on the base directory, and then from there users can create snapshots. Let's say somebody accidentally deletes it. Here we can see, if you look closely, the data for the 16th is missing. But you can still look back and run ls on the snapshot and see that the 16th is still present. And then from there you have the option of restoring that data from the snapshot. Next feature I'd like to describe is new in Apache Hadoop 2.7.0. We're enabling more reporting about data node volume failures. We used to expose a count for you, so you could tell how many volumes had failed in the cluster, but we didn't really give you any more detail than that. So what we've done is added some enhancements. On this screenshot, it's again the health summary page. The total data node volume failures there is a hyperlink showing you the total number, which then jumps to this screen, which is an entirely new screen. And this screen lists out more detail. It gives you the individual nodes with failures, and on each node, the path of each failure, an estimate of the total capacity lost, the date time of the last failure. And I envision a systems engineer using this screen as kind of a daily to-do list to figure out what needs to be addressed in the cluster. This is what it looks like when there are no failures. I included this because we like to feel good about ourselves and cross our fingers and hope it looks like this sometimes. Everything in the web UI, just as a general philosophy, we source it from standardized Hadoop metrics, exposed through JMX, and also exposed through a REST API. For this particular feature that I just described, the data node metrics are published both individually and in aggregate at the name node. And what that enables is, for us, we can integrate it into Apache Ambari so that there's one place to look for this kind of information. For you, if you prefer a different management tool, or if you want to roll your own custom ops dashboard, it's something you can very easily query and bring that data in. And one last look, this is showing another Ambari screen. There's more information about monitoring, alerts, all integrated into Ambari. And like I said, this information is all directly sourced from the HDFS cluster. So in addition to Ambari, you have integration options for querying that data from other places. So in summary, we talked about some common configuration mishaps. We talked about garbage collection issues, configuring for redundancy at the data node. We talked about retuning configuration periodically. We discussed the Hdfs Ackles feature as a way to help guard against accidental deletions, also Hdfs Snapshots. We talked about the new feature for reporting data node volume failures and how that can help administrators maintain a cluster day to day. And we talked about how a lot of these best practices are getting incorporated back into Ambari. So if you use Ambari, you're getting this information automatically. I left my email address up here. If you have operations questions or suggestions or anything else that you'd like to see exposed in metrics, for example, I'd really like to hear from you, so please feel free to email me. I've also left up some links to additional resources if you want to get a deeper dive information on some of the topics I discussed today. Thank you. Any questions?
Hi.
Hi.
I've noticed in an HA configuration for the name nodes, when the edit logs are stored on the journal nodes, there still seems to be a requirement that the Hdfs site needs to contain the path to the edit logs locally for the active name node.
Yeah, that's interesting. This came up, this was a question in a talk a couple days ago as well, and I don't think there's a strict requirement for that. I think part of what was going on there was the Quorum Journal Manager was initially developed, and just to be conservative, just to be on the safe side, we kept writing a local copy as well, just in case there was any instability in that new system. I think at this point it's something that's not really necessary.
Yeah, I just saw the problem that if it fails, then the name node goes down. So I was just wondering.
It does go down. You're observing that it does go down if that local copy?
Yes, if say that mount is not accessible, so
Okay.
it can't write to that location.
Okay. In that case, is it an NFS mount by any chance?
Yes.
It is, okay. There are some NFS options. Maybe you want to email me afterwards. There are some NFS options that are very important for that, basically for soft mounting, so that failure to write to an individual NFS mount won't block the entire name node process.
Gotcha. Sorry, another question. The snapshot folder, when you do Hdfs DFS count, the command seems to incorporate all of the files and folders that are part of the snapshots. I just wanted to know if that was kind of planned, because the Hdfs check command works in a different way, where it only takes into account the active folders in the files.
So I know that the count, there was a bug at one point where count was not checking snapshots, and that was fixed. If you're still seeing that on very recent versions of Hadoop, I'd like to know about that, because that might mean there's a regression. So if you do still have a repro for that, I would like to hear about that, and I'd appreciate it if you'd email me with that and mention what version you're running.
All right, thank you.
Thank you.
The problem you had before, the name node pointing to the wrong cluster, end up name node telling the data node to delete the undefined files. Would it help if you put the name node in safe mode? Will the name node still tell the data node to delete the unreferenced files?
I believe, let me think about that. I believe safe mode only is blocking user-driven operations at that point. And actually, we've got some other HDFS folks in the audience, as it turns out. Does anyone else know that for sure? I don't know the answer to that for sure. What about the deletes? The delete, if a file was already deleted and then the name node was restarted, do the block deletions? Okay.
Oh, okay. So save mode will save him if he didn't change anything. Okay.
Yep. Well, if there are no other questions, feel free to chat with me afterwards, too. Thanks.